A computer typically has several places where bits get stored, and we usually think of these storage locations as organized in a hierarchy. At the top of the hierarchy are the CPU's processor registers because they are the fastest locations in the whole system. When the program wants to use data, the most convenient place for it to get anything is if it's already in one of the processor registers. On the other hand, the processor registers are a low capacity storage location. They're very small, each individually, only a few bytes, and there's just not a lot of them. In contrast, at the bottom of the hierarchy, we have storage devices like, say, hard drives, which is where we have most storage capacity and very cheap storage capacity. Here in 2010, you can buy a terabyte hard drive for about $100. On the downside, the hard drive is the least accessible location for data within the computer, because when the program needs data off the hard drive, that may require spinning up the hard drive, seeking the head to the proper place on the cylinders, and then just transferring that data over some relatively slow bus channels. And then eventually we get the data copied into a register of the CPU where we can actually use it. But on the time scale of the CPU, that takes a very, very, very long time. Getting data off the hard drive is several orders of magnitude slower than using data that's already in a processor register. In between these two extremes, we have a couple layers, and the pattern holds that as we go up the hierarchy, the speed increases, but as we go down, the capacity increases. So for example, a system's random access memory is more than an order of magnitude faster than a hard drive, but RAM typically has much less capacity and it's much more expensive per gigabyte. Here in 2010, $100 will buy you about 4 gigabytes of RAM. Finally, in between RAM and the processor's registers, we have another level of memory, which we call cache. In today's systems, the processor's cache usually exists in the processor package itself, such that it's sitting right next to the CPU, where it can be very quickly accessed. The cache is typically made with a memory technology that is an order of magnitude or so faster than regular RAM, but on the downside it's much more expensive, and so partly for that reason we just have much less of it. So say where 2 to 8 gigabytes is typical for a new PC sold today, the total amount of cache in the same system is typically about just 1 or 2 megabytes. Now, what makes the cache interesting, and what gives it its name, is how the CPU actually uses the cache memory. Whereas the CPU reads and writes from the main system memory when explicitly instructed to by an instruction, the cache is read and written by the CPU as a side effect of these instructions to read and write the system memory. When the CPU reads stuff from memory, the contents of that memory also get copied into the cache, such that the next time the CPU reads those same addresses, it can actually look in the cache first, and it's likely to find that the content of those addresses are actually still in the cache, so it can just read the cache instead, which is much, much quicker than actually reading from the main system memory. The tricky part about this is that the hardware has to be careful that, say, we've copied some section of memory into cache, but then we modify that part of memory. Well, then we have to make a note that what is in the cache, that copy is no longer any good, because it doesn't reflect what is actually in memory at those addresses. The cache's copy has gone out of date. The neat thing about the cache, though, is that it's managed entirely by the hardware. As programmers, we really don't have any direct control over it, in fact. When the CPU caches stuff from memory, or when it reads from its cache, that all happens totally transparently to the programmer. In fact, there's no instruction we can give to the CPU to tell it to do something with the cache. The cache is managed entirely as a side effect of the normal copy instructions, the normal interactions with main memory. Despite our lack of explicit control over the cache, it can be very important for a programmer to be aware of the cache's existence and how it works. And the reason is this. In computationally intensive programs, a main concern of efficiency is making sure that the CPU always has the data it needs in a steady stream. Therefore, we want a CPU to be able to use its cache as much as possible without having to go out to the main memory. When the CPU has to get stuff from main memory, it's much more likely to have to sit and idle for some number of CPU cycles because it just doesn't have the data it needs. So, if we want the CPU to use its cache as much as possible, we need to arrange our program such that when the CPU deals with data, it should do so with stuff that is near each other in memory as much as possible, rather than constantly skipping around all around memory. The way caches usually work is that when the CPU reads from, say, address 100, the cache is not just going to grab just byte 100, it's going to grab everything around 100, say like 4,000 kilobytes around it. The cache does this because it's a good strategy. When CPUs read from addresses, they are very, very likely thereafter to not just read that same address sometime soon after. They're very, very likely to read the next bytes in memory near that address. So because of this behavior and the fact that the cache is only so big, it's only a small fraction of the size of the system memory, if our program tends to skip all around main memory, then what's constantly going to be occurring is what's called a cache miss, which is the situation where the CPU wants a byte from memory that doesn't happen to be in the cache, and so we actually have to get the whole memory system to engage and send its bytes to the cache where then the CPU can get at them. If instead our program tends to do a lot of its operations in one local area of memory, then you're very likely going to drastically reduce the number of cache misses. Now understand, in practice, writing code to avoid cache misses is really a very advanced technique. It's certainly not the sort of thing you should concern yourself early on in your programming education, but just understand eventually when it does come time to write some code that might be very computationally intensive, that's going to be one of your main concerns. It's just the nature of the modern processors that they're very, very reliant upon heavy uses of their cache to get the most efficiency.